our participation in the 8th undergraduate virtual research competition held by Abu Dhabi University. Our research title is the numerical and experimental analysis of liquid-liquid ejector for generation of water in oil emulsion. My name is Jabir Yami and I am presenting the research conducted during my undergraduate research course with my teammate Mr. Omar Salim, master degree student and supervised by Professor Abdessalam Al-Sirhi. Emulsion can be defined as thermodynamically unstable system of two or more phases, where the phases cannot be mixed with each other due to the difference of its properties, where the one phase is the external phase and the other one is the internal phase. Examples of daily used emulsion are milk, shampoos, and many beneficial medication. The emulsion types are generally for oil and water where the oil is the external phase, water in oil where the water is the external phase, and maybe sometimes we have multiple emulsions where oil in water and oil and water in oil and water. The macro emulsion has the droplets of size more than 0.1 micrometer and the micro emulsions has the size of the droplets less than 0.1 micrometer. The emulsion applications generally are the food industry, healthcare, cooling and lubrication, and the petroleum industry. The targeted application of the present research is to use the stable emulsion in the enhanced oil recovery process (EOR). Traditionally, several techniques are being used for generating stable emulsion and all mainly depending on the mixing, where preparing the emulsion, then store it to be used whenever needed, is called the batch preparation method. However, the batch preparation methods have several challenges where the emulsion is thermodynamically unstable and it will separate with the time, and the properties of the emulsion can be changed with the time and it will be expired and cannot be used, and at the same time it needs a storage system where it can be stored safely, and it has the lack of benefit of the fresh emulsion on demand. So, our proposal is to have inline generation technique based on the liquid-liquid ejector, providing online and on-demand fresh emulsion, simple and more reliable, and has no moving parts. In addition, no maintenance required. Then, our objectives in this research is to conduct a comprehensive review on the emulsion generation techniques, stability, and rheology behavior of the emulsion as well as ejector applications and modeling. Also, to investigate the effect of the ejector parameters on the suction flow rate and the performance of the ejector. Then, to access the applicability of using liquid-liquid ejector for generation of water-oil emulsions. Also, to study the effect of the emulsifier on the performance of the liquid-liquid ejector for emulsion generation. Finally, to study the external phase, stability, droplet size, distribution, and rheology of the generating emulsion through the ejector technology. The governing equation of the ejector in terms of the section flow and the pressure ratio, densities, and etc. is shown in this equation. This was used for the parametric study to perform this work. The experimental flow loop consists of suction tank, motive tank, pump, and discharge tank in addition to the control valves at all flow streams. The ejector experimental SCADA was designed based on the range of the flow meters, the available pressure, and the pipe diameters. Control valves and flow meters were installed at all flow streams to study the ratio of the dispersed phase and the external phase and control this ratio for the specific application. The experimental setup has mainly one ejector, 2 flow meters, 3 pressure gauges, 3 control valves, 2 motive inputs, 1 suction input, and 1 discharge output. In addition, in this slide, you can see the experimental flow loop with different views. Here you can see the ejector setup and the connection and valves and the flow meters and pressure gauges. For the measurement tool and techniques, we have measured mainly the salinity, resistivity, TDS, conductivity, temperature, and concentration. For the salinity measurement, we have used the portable conductivity meter. And for the emulsion external phase, we have used three methods where we have tested the conductivity test by the TDS, water drop test, and oil drop test. Note that our goal to have the oil as external phase, then our target to have 0 TDS and undispersed droplet on the water and dispersed droplet on the oil. And for the emulsion stability was tested and monitored by having samples at 25 degrees Celsius and also at 50 degrees Celsius, and report the percentage of oil separation, if any, from the emulsion with time for several hours up to 10 days. Emulsions were prepared at different water salinity, and stability was checked for different emulsions to check the influence of water salinity on the stability of the prepared emulsion. In some cases, we have tested the emulsion at different salinities and percentage of surfactant, and we found the formation of sub-emulsions. We have performed the conductivity test and the stability test and the droplet size distribution test and made sure that the external phase is still oil. We performed viscosity measurement and rheology study for all generated water and oil stable emulsions using cylindrical rotational viscometer. The rheological study for all generated water and oil stable emulsion at different water salinity and surfactant percentage conducted as shown in the figure at different temperatures at 25 degrees Celsius and 50 degrees Celsius, where in the x-axis we have the shear rate and the y-axis we have the viscosity. However, in this figure and this slide you can see the shear rate at the x-axis and the shear stress in the y-axis for the same conditions of the percentage of surfactant and the salinity. Droplet size image and distribution were measured through using the Leica DM2000 optical microscope. Droplet of water and oil images were taken and analyzed to get the droplet size and its distribution. The median size of the upper emulsion is 1.8 micrometer, while the median size of the middle emulsion is 7.82 micrometer. 90% of the droplets in the upper and the middle emulsion are lower than 11.16 micrometer and 17.67 micrometer respectively. In this slide you can see the droplet water test and the droplet diesel test for different surfactant percentage, where oil doesn't dissolve in the water and dissolve in the diesel, giving the indication that oil has the external phase as diesel, but with different ratios of separation. This table shows that we were able to generate any percentage we required for the dispersed phase in the external phase, up to 70% of water and 30% of oil, the percentage all under our control. To conclude, liquid-liquid ejector is an effective technique for online generation of emulsion. Increasing the motive stream pressure dramatically increases the suction flow rate, while increasing the density ratio gradually decreases the suction flow rate. Motive suction stream fluid has no impact on the external phase of the generated emulsion. Water TDS plays the main role in determining the continuous phase. Water salinity has major impact on oil and water emulsion stability and minor impact on the water and oil emulsion. All generated emulsions are more stable at room temperature than at 50 degrees Celsius. The stability of the generated emulsion is a function of the surfactant percentage. The ejector technology has the potential to generate stable water and oil emulsion up to 60% of water volume fraction or more. Thank you for your attention, and please contact us for any information in the below emails.